So welcome back to part 2 of our lecture 3 on subspaces. So in the last part, I just gave us a theorem about that will allow us to check whether a subset is a subspace or not. And I want to give two examples in this little part of in part 2 to show you how to use the theorem. So here's my first example that I want to look at. I have a vector space V, which is F3, and I am taking the set of all triples inside of F3, where x1 plus x2 plus x3, if I take the sum of the coordinates, I get 0. And what I want to do is I want to show that W is a subspace of the vector space V. And the interesting thing to note here is F could be the real numbers or it could be the complex numbers. And this set over here will still always be a subspace. So what we need to do is just check the three conditions. Here, I'll move it back over here just so you can see for a second. We need to check, is 0 in the set W? If I add two things together in W, do I get something back? And if I add something, take something in W, multiply it by a scalar, do I get something back inside of W? Okay, so let's run through that. So is 0 inside of W? Well, you have to, when you're doing these questions, you have to think about what is the 0 vector inside of my space? Well, the 0 vector is the tuple that consists of all zeros. And then it's clear that this is inside of W because 0 plus 0 plus 0 is equal to 0. And 0 plus 0 plus 0 equals 0. So the vector containing all zeros is in the set W, and the vector containing all zeros is the 0 element. Okay, so that part's good. Now we want to take two elements in my set, and I want to add them together. So I'll take two arbitrary elements inside of W, and so what I know about these elements is that X looks like a triple, X1, X2, X3, and Y is also a triple, Y1, Y2, and Y3. And because they're in W, I know that if I sum the coordinates of both of them, I get that they sum to 0. So now I want to look at the vector x plus y. Then x plus y, well, by definition, what I'm doing is I'm adding coordinates, I'm adding the coordinate, the vector's coordinate y's, x2 plus y2, x3 plus y3, and I want to check to see if this is in W. But now what we notice is that x1 plus y1 plus x2 plus y2 plus x3 plus y3. I can regroup this, right? So I can put all the x's together. I can put all the y's together. And I know that the sum of the x's is 0, and I know that the sum of the y's is 0, so this whole thing is equal to 0. So this tells me, so the sum of my two vectors is inside of W, which is part of it's what I needed to show for this fact. So if I take two vectors and they sum up and they take the entries and they sum up to 0, and I add those two vectors together, I still have a new vector with those properties. And finally, we need to check the third condition, which I think I have some room over here. So here I take a vector x in W and I take some scalar inside of F, and I just write out what does it mean for x to be in W. So x is equal to x1, x2, x3. It's a triple. And I know that if I sum up the entries, I get 0. Okay. Well, then I want to know what happens if I take c times x. Okay, so by definition, that means I'm multiplying each of the coordinates by this constant. Right? And I want to know if it's in W. Well, I take cx1 plus cx2 plus cx3. These each have the constant c, so I can factor it out. So I have c times x1 plus x2 plus x3. But we know that x1, x2, x3 is 0, so this is c times 0, which is equal to 0. So cx has to be in W, and we now write our conclusion. Thus, W is a subspace of my vector space V because it satisfied all three of the conditions. So you'll see these sorts of problems over and over again. It'll ask you, show something as a subspace. And this is how you would do it. Okay, you first check to see if there's 0 elements in there. You then check to see if it's closed under addition, and then you check to see if it's closed under scalar multiplication. Here's a more complicated, or well, not more complicated, but a different type of example using a different vector space. So we talked about this notation last time. Our vector space is going to be R raised to the power of the closed interval 0 to 1. And we introduced this last time. This is the set of all real valued functions from the closed interval 0 to 1 to R. So these are functions that you looked at in calculus. And now there's lots of different functions here. But what we're going to do is we're going to pick out any of those functions that where f is continuous. Okay, so maybe this will help you. So this is on the set of all f such that f goes from 0 to 1 to r, and then f is continuous. So things like polynomials would be in here, or sine x or cos x. These are all examples that are continuous. And the claim is that you have this large vector space that C is a subspace of V. Okay, so what we're going to do is just check the 3 criteria. Okay, and here is the proof. First of all, we have to think about, well, what would be the 0 element in this vector space? Well, the 0 element of our vector space is just simply the 0 function. It's the function that takes every vector and maps it to 0. Okay, so the 0 element is a function, and it's a function that maps every element on the interval 0 to 1 to 0. Now, if you were to draw this in calculus, right, it just means you would have a line at the horizontal axis, and you should be able to convince yourself from calculus that this is a continuous function. So yeah, 0 is the 0 element of V, also belongs to C. Okay, so the first part's okay. And now let's talk about the other part. Okay, so let's take 2 functions, f and g, inside of my set of continuous functions. From calculus, we know that if f and g are continuous, then we know that their sum is also continuous. Right? So we're using some calculus here in linear algebra, so that the sum of 2 continuous functions is still continuous. But since this is how we define the sum of elements in V, we have that the sum of f and g belongs to my set of continuous functions. And here's another example. Let's say I take a continuous function and I take some sort of scalar lambda inside of my field. From calculus, we know that if you take a continuous function and you scale it by a constant, you're not destroying the continuity. It will still be a continuous function. Right? So if f is continuous, then lambda times f of x, which is equal to lambda times f of x, is continuous. So lambda times f is also inside of C. So C is a subspace of V. Okay, so this is a little bit more complicated example, but you notice that the structure is the exact same. You have to know what the 0 element is, check that it's in there, take 2 elements in there in your set, and check to see if their sum is also inside of it, and take an element inside of your set and multiply it by a scalar and see if it continues to be inside of your set. So it makes it a subspace. So this is kind of 2 good examples to show you how to check whether something is a subspace or not. We'll take a break here, and in the next part we'll talk about taking subspaces and starting combining subspaces to make bigger subspaces.